Hey guys, Misty here with a new video about an interesting topic. Today we are going to talk about multi-armed bandit problem. It is something like the foundation of reinforcement learning, as many of the problems and phenomena prevalent in reinforcement learning can be easily explained and illustrated in this rather simple setting. I guess most of you are familiar with the concept of one-armed bandit. It is a slot machine where you pull the lever and wait for the result. Sometimes you receive a reward, sometimes you do not. It is a hazard game, obviously. In the multi-armed bandit problem, we have more than one such a single-armed bandit. Each of them have its own distribution of rewards, although some of them may be identical. They are all framed in one environment we interact with through the choice of actions to take, where the action means pulling a certain lever. It shows that such a model is very useful in many experimental fields. So how does it work anyway? The choice of action leads to interaction with the environment, which produces a new reward. When we are talking about rewards, we restrict ourselves to scalar values. The reward is specific for the action we have performed, thus it provides some information about the reward distribution belonging to this action. Our goal is to interact with the environment in such a way that we maximize the sum of rewards we receive. In each time frame, we select one action based on some sort of strategy. Then we interact with the environment, which produces the reward, and then we move to the next time frame. This process repeats itself for as long as it is necessary, and the duration may be different for different applications. We would like to compare the distributions among the actions, in particular with regards to our goal, which is to maximize the cumulative reward. A useful piece of information for this purpose would be the expected reward for each action, that is, the expectation of the action reward distribution. The rewards received for different actions are samples from their reward distribution. If this process would go to infinity, we would receive the complete distribution and we would know everything we need. However, usually we cannot do that and we need a different approach. If we have only a few samples from the distribution, we can estimate the quantities we are interested in. That is, we are going to calculate the value q of some action ai, which is the estimate of the true value qi. The simplest method for the expected value estimation is the sample mean. The brute force method stores all of the observed rewards of one particular action and then calculates the average. More sophisticated method allows us to remember just the average from the last epoch and update it based on the new observed reward. So each time we receive a new reward, we estimate a new estimate of the action-specific distribution mean. We can implement the brute force method quite easily, and the advantage is that such a function has only one argument. It is a list of all observed rewards, including the newest. However, as the times go by, this list will grow and eventually it may even not fit into the memory. The update method requires us to remember three quantities: the old mean reward estimate, the newly observed reward, and the number of observed rewards, including the new one. Note that for this calculation to make sense, all the three quantities must relate to the same action. Once we have some estimates for action values, we can perform the action selection, which will drive our interaction with the environment. The selected action at time t is the action for which we have the maximal value estimate. This is called exploitation, as we rely on the information already collected from the environment. Exploitation is a very important aspect of all reinforcement learning because it is supported by our current understanding of the environment. Without any advanced Python packages, we can assume that our value estimates are stored in a simple list. To get the maximum value, we can enumerate the list, which gives us a series of index and value tuples. The value is used as a key, however, we explicitly return the 0th element, which is the index of maximum. So far, the action selection was based on the estimated action values. However, as the rewards are either completely or at least at the level of modeling random, our estimates in the first steps may be very misleading. Therefore, we need some mechanism which would allow us to have some room to explore the other actions, despite them not having the largest action values. We select some arbitrary probability epsilon, with which we pick the next action randomly, instead of based on the action values comparison. In combination with the previous approach, this algorithm is called epsilon greedy. The approach presented so far can be summarized into a simple algorithm. At the beginning, we initialize our action value estimates. The initial values do not have to be 0. We also initialize the number of observed rewards, denoted by n0 of a, to 0 because we have not observed any reward so far. Then we step through the time. By the action selection process described previously, we select one action to perform. By performing the action, that means by interaction with the environment, we observe a new reward, which we then use to update our estimate. The numerical estimates provided by this algorithm do not reflect how good the estimate is. The quality of the estimate depends, for example, on the number of action samples. Also, if the distribution would be non-stationary, the time since we have observed last action reward has its impact on the estimate quality as well. The previous method was introduced as mean estimation from reward samples. From statistics, we know that we can also estimate the variance of the sample mean. Standard deviation of the sample mean is equal to square root of ratio between the population variance and the number of samples. In the multi-armed bandit setting, we call this upper confidence bound. The action selection process is influenced not only by the action values, but also by the standard deviation estimates. The quantity nt of a is the number of times the action A was performed up to time t. The quantity c is a parameter of choice, and there are two possible interpretations of it. It is our estimate of the amount of spread of rewards the actions provide. But it can also be interpreted as the confidence-bound distance we want to take into account. That means how far from the sample mean we want to look. The resulting formula replaces the action selection part of the complete algorithm. Imagine for a moment that we can estimate the action selection probabilities. These can then be used for the action selection, which would make different algorithm than we have presented so far. Let us say that we can estimate at least action likelihoods or preferences. In the machine learning setting, we would know how to transform such values to probabilities. For this purpose, the softmax function is used. The question that remains is how to calculate the preferences. The action at time step t is selected according to the action probability distribution, and in reality, it could be any probability distribution we would like to have. The action preferences ht of a are updated each time a new reward is provided by the environment. The difference here is that we update both the action AT we have selected and all the other actions. The core of the update is the difference between the observed reward RT and the baseline reward calculated as the average of all the observed rewards across all actions so far, except the last one. This is multiplied by the learning rate alpha and multiplied by the probability of the rest of the actions for the action selected, or by the probability of one particular action for the others. The preferences calculated this way are then fed to the softmax function, which transforms them into the probability distribution, which is used to generate the next action. Note that the update rules are based on the maximization of the expected reward, which is our goal within the Multi-Armed Bandit problem. We could implement the softmax transform very easily. The math module provides us with the exponential function. To prevent performing the summation multiple times, we pre-calculate it and then use it in the denominator repeatedly. In the implementation of the gradient update, we utilize the softmax transform from the previous slide. The preferences from last steps transformed into probabilities are used in the update calculation. Note that we do not put any restriction to the learning rate parameter. However, in reality, we would need it to be larger than 0 and smaller than 1 in order the algorithm to converge. So what did you get from this video? Now you know that Multi-Armed Bandit is a nice illustration of the reinforcement learning exploration-exploitation problem. There are multiple approaches to this problem. Each of them performs some kind of estimation. Overall, the problem is very easy to understand and to apply the methods described. With the code illustrations provided in this video, you can definitely try it for yourself right now. Thanks to all of you for your attention. If you liked the video, go and hit the like button, and maybe even the subscribe button so that you do not miss any future interesting videos. This was Mystic, and bye for now.